cannot direct the wind, right? But we can adjust the sails. So I want to show you one of these examples in the context of data centers. So data centers have a lot of workloads these days, also from machine learning, and I want to show you an opportunity there that currently gets a lot of momentum. So we have many applications running in the cloud now, right? We know this is a big data center from Facebook, but there are bigger ones. Related the applications to medicine, social networking, gaming, and I guess even you this morning have used some of these applications already that are running in the cloud there. So actually the applications there are highly distributed, and that also means that they have produced a lot of communication traffic. So traffic grows explosively in data centers. And these networks in data centers are becoming a critical infrastructure of our digital society. This is a nice visualization that a colleague of mine at KTH did. If you think of each of these drops to be an IP packet, then this is something like what a single router in a data center has to handle. Okay, so these drops as amount represents the traffic in a single router there. And the problem here is that currently we have this Moore's law everywhere, and this Moore's law also applies in networking. And network equipment is actually reaching capacity limits. So transistor density rates are stalling, power density rates are stalling. So we need actually more and more equipment and larger networks there. And this is quite resource intensive and inefficient. So, and I want to show you one of the reasons why this happens, and we also will see what's currently happening to solve this issue. So one cause is the way we interconnect racks or servers or GPUs in a data center. Okay, so typically a data center today is similar to a tree structure. Okay, it's like a clause topology, or there are different flavors, but all of these networks, they are fixed and oblivious to the actual demand. So they don't change. They have been built once, and they are there. And that's a little bit like building a highway that ignores the actual traffic, right? It can be very frustrating. You're in the traffic jam on the right, but there is a lot of capacity on the left. So it would be nice to be more flexible here and to be like more demand aware or traffic aware. And that's actually a vision that is slowly coming also in the context of data centers. So now, imagine again you have these 8 racks here, and you could interconnect them in a different way, in a flexible way. So imagine you had mirrors at the ceiling of the data center, and you have something like a laser on the rack. And then if you have a traffic matrix that looks like this, where rack 1 communicates to rack 5, and rack 2 communicates to 6, 3 to 7, and 4 to 8. It would be very good if you could interconnect the data center so that it directly matches the demand. So we directly connect rack 1 to rack 5, 2 to 6, 3 to 7, etc. Maybe later the traffic demand changes. So, and then again, you would like to have an interconnect in the data center that matches this demand. And that's like the vision of demand-aware networks or self-adjusting networks. Okay, so actually there is a nice analogy that maybe you know it in San Francisco. They have this Golden Gate Bridge, and they have the Golden Gate Zipper. This is this yellow car that can change the number of lanes during the day. Okay, so if you not familiar with it, it like drives across the bridge, and then it makes out of 4 lanes to 2, it can make different number of lanes on the different sides. And that's like the vision that we want to have also in data center context. So now the motivation here is that actually traffic and communication patterns in data centers are quite structured. So they are sparse and skewed. So these are studies by Facebook and Microsoft. And they also have a lot of structure over time. So they're bursty over time. And if you can build a data center network that exploits this structure, that can be very helpful. And I plot here to see different structures of different workloads, a 2-dimensional map. It's called the complexity map. And on the x-axis, you can see the structure over time, or the complexity over time. So structure and complexity is the opposite. And on the y-axis, you have spatial structure. So like how skewed is this traffic pattern? And here we have something like database cluster from Facebook. We have a web cluster from also Facebook. Then we have a batch processing application that had Hadoop here. And we have a machine learning workload, and we have different high-performance computing workloads here. And if you map those onto this plot and see how much structure they have, you can see that different applications have different structures. Okay, so for example, on the right, you see the different Facebook clusters. So they have quite a bit of spatial and temporal structure. But for example, neural networks. On the lower left, you see the neural network. So this has actually a lot of temporal and also spatial structure. So it's very skewed traffic that is very different from uniform or random traffic that would be here on the upper right. Okay, so different application workloads in data center have different structures. And actually also, if you, I'm not sure you are familiar with this, but if you have like a heat map of the communication traffic, you can cluster it using bi-clustering algorithms. So that allow you to see like what kind of clusters exist in the data center. And also here we can see it's highly structured. So we have a lot of small clusters, and the clusters don't evolve so much over time. So we really don't have a random traffic, but we have much more structured traffic. Okay, now you may think this sounds crazy. Why do we think even about adapting the data center network to such structure? But there is emerging technology, and this technology is coming in many fields. So it's coming in networking, it's also coming in storage. For example, Microsoft, they have a huge project about this. I'm talking about photonics. Okay, so there are these sayings that photonics are one of the 5 key enabling technologies for the future prosperity in Europe. And also I found this nice quote from the National Research Council in the US, where they were saying the photons are the new electrons. So there's a lot of hope in photonic technologies. And again, for storage, but in our case also for networking. So there is actually a spectrum of different optical routers that we can see on the market now, and also in prototype stage. There are routers that have something like a moving antenna, where you can change the interconnect by moving an antenna. But this is quite mechanical, and it's relatively slow. But then there's technology based on moving mirrors, so you can basically program micro mirrors, and you can change the propagation within microseconds. And now, actually also by Microsoft, they have this tunable laser technology that you can change the color of the laser, and then you can change the interconnect. And I want to show you just 1 and 2 examples a bit in more detail. So these lasers are not going in free space in the data center, but they're inside a router, okay, inside a box, an optical circuit switch in this case. So if you have a light coming in through the fiber into this device, here, then it goes to a mirror, and it will be reflected on the mirror, it will be reflected there, and it can go out there. Okay, now if this router has movable mirrors, or mirrors that you can program, then you could change the angle of this mirror, for example, like that. And now if the light enters here, it will be reflected differently, and it will actually go out through the middle port. So you can dynamically change the interconnect by changing these mirrors. Another really interesting technology is this tunable laser technology, where you can change even in nanosecond speed. It's roughly, you can think of it like that. You have like a laser source again, and then you can change the color of the laser. And depending on the color, it will go a different path. And this is like, you can think of it like a prism. So if you have a prism and you would send a red light into this prism, it will go out there. If you have a prism, you have a blue light going out, it would go out there, because the prism fractures it in a different way. So these are just 2 technologies. And one real-life example is Google Jupyter Data Center, where basically you can already reconfigure parts of your network with this technology, with optical circuit switches. But there are others as well, but this is like one of the pioneers in the field. Okay, so that's roughly the big picture. So on the one hand, we have this flexibility in the technology. But now we also have this structure in the traffic patterns. So if we could bring this together, we could make data centers more efficient in terms of performance, in terms of energy efficiency, etc. So when you think about our nice plot again, on the upper right is traffic that has no structure, is uniform traffic. And on the lower left, for example, there is this neural network traffic. So today we build our data centers for the upper right, but if we could build our data centers tailored to the traffic pattern, we could gain a lot, right? So on the upper right, we have today's data centers. On the lower left, we could have these reconfigurable data centers. And of course, in many fields now, we see networks or systems that become self-adjusting and demand-aware. Like algorithmic trading is an example. Also recommender systems, for example, of Netflix, they are adapting to your taste. Also neural networks, of course, they're also self-adjusting systems in some sense. But here it's really about the hardware, the physical layer that becomes self-adjusting. And there is actually a nice design choice we have here. And on the one axis, we can have data centers that are demand-oblivious, that are not optimized to the demand. So this is like the data center we have it today. But then we have this vision of demand-aware data centers where the topology can really adapt to the demand. But there is another axis that is completely independent to this axis, which is whether the data center topology, the network, become dynamic or whether it's static. And today's data centers, basically, they're all demand-oblivious and static, as I mentioned. And interestingly, I told you about this upper right, where data centers become dynamic and demand-aware. But very early prototypes and also startup company was happening in this corner, which was surprising. They built data centers that are dynamic, so they changed the interconnect, but they're demand-oblivious. So that was quite surprising to many people, including us. Why do they build a data center that is dynamic but not optimized to the traffic? And you will understand in a second. And then there are these demand-aware dynamic data center networks. So we have static networks, we have networks that change very fast in oblivious manner, and then we have these demand-aware networks. And then you can ask, what technology is now the best one for us here? And as always, in computer science, the answer is it depends. Okay, it depends on the traffic. What is good about these demand-aware networks is like if you have a very big flow, so they call this elephant flow. If you have a big traffic going from the very left of your data center to the very right, so this is this red flow here, that will consume a lot of bandwidth because you go all the way through the data center. So it would be much better if you have a direct connection or only a single hop, and then the flow goes over that. That can save a lot of bandwidth. But there is a disadvantage of doing these adaptations. So it takes time to adapt the data center. Okay, so that's something we have to trade off. On the one hand, we have this bandwidth tax. We have to pay a lot of bandwidth if we don't adapt. But on the other hand, if we want to optimize the network towards this demand, we have to adjust it, and this takes time. So we have something like latency tax. And now the question is, okay, which technology or which data center flavor is the best for these different traffic types? And you can think what kind of traffic types exist today. And those of you working in networking, I guess they have seen these different flavors that we list here. So one of them is, for example, if you have batch processing applications like MapReduce or Hadoop, or actually many batch processing applications have shuffling phases where you shuffle data around. It's like all-to-all type of traffic. But then, for example, machine learning patterns, they are different. So for example, all reduce operation, they have more like tree type of traffic patterns or ring type of traffic patterns. And query traffic is often, queries are very small requests or messages, and these are called mice flows. Okay, so this is a different type of traffic. And then we have also something like control traffic. We want to learn about the data center infrastructure, and we gather all this information from the different places. So these different traffic patterns and applications come with different requirements. So some of them are very bandwidth hungry. For example, these machine learning applications. But some of them are also latency critical or latency sensitive. For example, this query traffic. So we need to find a way to optimize the data center, choose the best technology for those specifically. So you could ask, if you have delay-sensitive traffic, will it be useful to serve it in a data center that is demand-aware, that is optimized towards this demand? And the answer is, I don't think this is a good idea, because if you have traffic that needs to go very fast, and you first want to optimize your data center, and first of all, you do the optimization, the computation, and then you do the adjustments of the topology, this will take too long. By that time, you could have transmitted this flow over a static network much better. So this tax is too high. The latency tax is too high. But what about machine learning? So if you have a machine learning workload, will it be a good idea to serve it over a static network? So again, machine learning, they have these very big flows, elephant flows, but not many of them, but they have a small number of those. Serving that on a static network will not be optimal, because we have to transmit it over multiple hops. So that one will really benefit if you would make it over demand-aware. So here the cost, the bandwidth tax would be too high. So ideally, you can think which traffic should go on which flavor of data center. And a first guess could be something like that. So shuffle traffic that has not a lot of structure, we should serve it on dynamic demand-oblivious networks, because there we have direct connections periodically, and we change very fast, so we actually have a very good throughput. And that's why in California they developed this RotorNet, for example, which later also became a startup company that was really just there for shuffling a lot of traffic in the data center. But then, again, demand-aware elephant flows, it's really worthwhile. You can amortize the optimization. You can amortize the change in the network for a big flow, because afterwards it will run quite a long time. OK. Yes. So that's one match that could work. Of course, I just give you the tip of the iceberg here. So I talked to you about how to change the network and when is it good to change the network for which kind of demand. But of course, if you change the physical infrastructure, you get a lot of potential problems, because you can say, OK, what happens to the routing? What happens if a link is not there? I need to do buffering. What happens to congestion control algorithms? So currently we have TCP congestion control that works very well. So if I start to change the network, all the assumptions of these protocols are no longer valid. So changing the underlying physical infrastructure can make a shock wave through these layers. Nevertheless, people started to have solutions for those. In the case of Google data center, they don't change the data center very often. So they change it like once an hour or so. But already there, they say it's quite beneficial. We actually recently made interviews. So if you're interested to see more details here, we made an interview with Amin Wadat, who was one of the leads behind bringing reconfigurable data centers to Google. And he actually said they would be very happy to make data center reconfigurations faster. But the issue currently is like the control plane. So if you need to control and make these optimizations and changes, so how can we make a scalable control plane? You need to learn about the traffic patterns. Maybe for some traffic patterns, you can already predict how they will look in the near future. But nevertheless, you need to have some kind of control plane that is currently still a bottleneck. So we also made interviews, by the way, with optical experts like George Papin. So you can also read about the technology there more. And also Manya Gobadi. She is like one of the leaders there at MIT, also building prototypes, for example, for free space optics, like reconfigurable data centers that are not inside a box, but that go through the air, basically. If you are interested, excuse me, we also have this course online where you can get to know the technology better, the models behind it, and so on. And also, if you're interested in the data that we use in these evaluations, and also to see like what structure the different traffic patterns have, we actually started collecting all this available data to researchers, for example, from Facebook, high-performance computing, and different data that's around on a project website. So you're welcome to take a look there and use it for your research. We have the problem that not all of us have the insights that a big company like Google has in their data centers, but nevertheless, there are some good sources for modeling this traffic and reproducing it. Okay, that's already all I wanted to say. So if you have any questions, I have some backup slides. We can go deeper, but I think that was the main idea.
But first, thank you, Professor Stefan Schmid.